Most lake visitors step right over the signal without ever noticing it. A subtle darkening of shoreline sediment that, under closer inspection, suggests the quiet settling of denser minerals. This shift in color, often to grayish-black, rust-red, or deep olive, marks more than just organic matter. It flags a hydrodynamic phenomenon that sorts materials by weight, and in that sorting process, gems can quietly accumulate. Unlike in riverbeds, where flow constantly redistributes material, lakes act as long-term collectors, letting heavy elements, including gemstone-bearing detritus, settle into stillness. In many lacustrine environments, the key lies in the interface zone, the transitional margin between water and exposed shoreline. Here, slow laps of wave action perform low-energy winnowing. If you dig just 5 to 10 centimeters below the surface in these darker bands, you may uncover heavier grains that remain after lighter silts and organics have been washed upward or inland. These grains, often angular, sometimes with unexpected color flashes, demand attention. What seems like ordinary sand can include spinel, garnet, or even microdiamonds, especially in regions with upstream kimberlitic or metamorphic influence. The mistake most people make is focusing only on brightness. Diamonds, for example, in their rough state, often lack the fire of a cut stone and may appear dull or greasy. But that's precisely why the sediment matrix matters. Look for tightly packed finds with unexpected heft. A patch of gravel that feels denser than expected when scooped. Once isolated, even a small concentration of heavy grains can be dried and sifted with a basic magnet to pick up magnetite or ilmenite. Their presence doesn't confirm a diamond, but in certain terrains, they're the breadcrumbs pointing the way. Some lakes, particularly those fed by glacial melt or cutting across ancient volcanic belts, act as passive traps for a surprisingly wide array of mineral fragments. Sediment cores taken from places like northern Saskatchewan or Finland have revealed grains of pyrope garnet and chromite, both classic diamond pathfinders, lying just beneath the surface waiting. It's not about depth, it's about pattern. Once you learn to read the topmost layer, every beach becomes a map. But how do you separate real candidates from the overwhelming volume of sand and stone? The next step doesn't require a lab, just light, observation, and one very telling physical trait. The first distinction that most overlook can be seen in the way light plays across a surface. While quartz and feldspar dominate most lake sediments, their dull, vitreous sheen contrasts sharply with the occasional glint of something anomalous. True indicator minerals, such as garnet, spinel, or even corundum fragments, carry a luster that resists matte dullness. They flash subtly in angled sunlight, not with sparkle, but with depth. This isn't jewelry store brilliance. It's more like the oily gleam of a stone that shouldn't be there. Dragging your fingertip across a gravel patch may yield another cue: resistance. Denser stones often feel smoother or more slippery under pressure, a tactile illusion caused by their lower surface friction. Combine this with visual luster, and you begin to filter your samples in real time. Pay attention to translucency too. Many gem-quality minerals transmit light along thin edges. Hold a suspect fragment up to the sun. If a dull pebble suddenly reveals a red or orange core, it could be almandine garnet or a related species. This process, though simple, introduces field-level triage. It separates the common from the curious, allowing a prospector to decide what to examine further. And here's where it gets counterintuitive. The most promising pieces often look less dramatic than the decoys. For instance, common quartz can exhibit rainbows and brilliant refraction, but it's light, soft, and low value. In contrast, a squat, dark red crystal with a conchoidal fracture and glassy luster may lack drama, but indicate high-density mineralization, especially if found in groups. This stage favors trained intuition, but even novices can build a reliable eye with repetition. A practical tactic is to lay out 20 collected stones on a neutral background and rank them not by beauty, but by luster, weight, and translucency. Eliminate the brightest and most colorful first. They're often glassy quartz. What remains may surprise you. Heavy, muted fragments, some metallic, others waxy or semi-transparent, are the real candidates for testing. They won't sparkle, but they might signal the hidden presence of something valuable downstream in the system. Once your eye is calibrated, the question becomes geological. Why do certain lake zones concentrate these materials? And why does still water hide such disproportionate mineral value compared to flowing streams? The answer is in the invisible current of time. Still water doesn't erode, it collects. Lakes function as geological archives, quietly accumulating particles over decades, centuries, or even millennia. Their shape and flow dynamics, though subtle, guide how and where these materials settle. Unlike rivers that wash away lighter and heavier materials alike in dynamic pulses, lakes allow gravity to separate and concentrate the densest fractions, often just meters from the edge. In this calm, overlooked silence lies the reason many high-density indicator minerals and occasionally gem fragments settle in specific strata beneath the surface. Older lakes, especially those formed in glacial kettles, tectonic basins, or volcanic calderas, show this pattern most reliably. These depressions often receive input from upstream rock formations, particularly metamorphic or ultramafic zones that shed garnet, ilmenite, and other heavy minerals. Over time, seasonal inflows sort these fragments by density and drag, forming enriched pockets in depressions, underwater benches, or beneath silt caps. If the lake has existed long enough, and if its inflow includes weathered kimberlite or serpentinized rock, it becomes a passive concentrator of gem-bearing residue. One key trait is the lake's geometry. Shallow, elongated basins with multiple feeder creeks are more prone to internal sorting, especially at points where inflow slows and drops its heaviest load. These locations may not appear remarkable on the surface, but underwater, just beyond visible drop-offs or where the color of submerged sand shifts, a hidden shelf often forms. On these ledges, heavier fragments accumulate while suspended silts flow over and settle deeper into the lake center. This sorting logic also explains why some lakes produce high readings for spinel, garnet, or zircon in bottom sediments even when no outcrop is visible nearby. The watershed may extend miles upstream, carrying mineral fragments in trace amounts over time. And while pearls, unlike diamonds or garnets, originate biologically, they too collect in low-energy pockets. Freshwater mussels, which form pearls, thrive in stable zones with soft sediment. So the same hydrological calm that concentrates mineral indicators can, in rare cases, harbor biogenic gems as well, though their formation requires entirely different conditions and much more luck. The silent sedimentation process leads many to underestimate these environments. But the clue is in the fines, the finest silt layers, often layered like quiet years in a tree ring. Beneath a thin crust of clay or organic film, those sediments can hide what no surface scan reveals. Crystals sorted by weight, enriched by time. But locating the exact zones where these deposits concentrate requires more than a trowel. You need to read the topography beneath the waterline. What lies just below that silty shelf? And how can you detect it without diving or draining the lake? The answer begins where current meets stillness. The confluence zones and drop-off shelves, where gems rest undisturbed. In every lake system with tributary inputs, there exists a zone of dynamic transition. A place where the moving energy of feeder streams collides with the still mass of the main basin. These confluence points are quietly violent on a geological scale. As fast-moving water slows, its ability to carry heavy particles collapses. What's left behind often includes the densest elements in the system: magnetite, ilmenite, garnet, and, under exceptional circumstances, diamond fragments, or sapphire detritus. These underwater drop-offs and deltas are the first places to examine when narrowing your search. The drop-off zone, where shallow water abruptly deepens, functions as a natural trap. Heavy material rolls just far enough before momentum stops it cold. In many lakes, this point sits just beyond wading depth, often 1 to 3 meters offshore, depending on slope and sediment composition. Use a long-handled scoop or a PVC-capped sampling pipe to extract a vertical column of sediment. If you notice a sudden textural change, gritty fines shifting to dense gravel or coarse sand, you've likely intersected a concentration layer. Another key terrain feature is the submerged bench, a flat zone formed by wave action and seasonal water level changes. These benches act as sorting tables. In late summer or drought conditions, they may even emerge temporarily, exposing black sands or oddly colored gravel patches. Red garnet fragments and greenish chrome diopside may become visible with a simple rinse. If visible crystals appear alongside magnetic minerals, it suggests upstream ultramafic or metamorphic origin, exactly the right ingredients for gemstone transport. Not all drop-offs are created equal, however. Feeder streams that descend rapidly through rockier terrain before reaching the lake deliver a different sediment mix than slow, meandering inputs through farmland or clay. The best confluences are where high-energy tributaries carrying coarse load meet steep-walled, sediment-trapping lakes. In these places, field researchers often record high concentrations of indicator minerals within a 5 to 15-meter radius of the stream mouth, especially on the flanks where lateral dispersion occurs. Still, accessing these zones requires caution. Shifting mud, submerged vegetation, and sudden slopes create serious safety risks. Always work with a partner and use a marked pole to probe depth and substrate consistency before wading. Avoid sediment-disturbing footwear that clouds your sample area. Instead, work from a low-impact raft or floating platform, allowing clearer retrieval. Waterproof pouches and sieves help maintain sample integrity as you shift materials through stratified trays, isolating the heavier grains. Once you've gathered material from the right depth and terrain, the next tool is shockingly simple yet deeply revealing. A basic magnet, swept through both dry and wet sample contexts. What sticks, and what doesn't, can pivot your investigation. But that distinction only matters when you understand how environment affects the read. In the field, a magnet is often underestimated, a rudimentary tool that, in expert hands, becomes a decisive filter. But its effectiveness isn't just about attraction, it's about where and how it's used. A dry sample magnet test might produce minimal results, leading some to abandon promising ground. Yet the same sediment, when wet and freshly extracted, often yields a markedly different response. The secret lies in saturation and grain contact. Wet conditions allow magnetically susceptible minerals like magnetite and ilmenite to cluster more tightly and respond faster to a passing magnetic field. To test properly, begin by drying half of your sample under sun or low heat. Ideally spread thinly on a white tray or tarp. Once dry, use a neodymium magnet encased in plastic or wrapped in a thin poly bag to sweep across the surface. Watch for immediate clustering of black grains, especially those that slide cleanly rather than jump. These are likely magnetite. Ilmenite, slightly less magnetic, may cling weakly or follow with delayed motion. Now repeat the sweep on the wet portion. You'll notice a more pronounced response, particularly in fine-grained concentrates, because the water minimizes particle dispersion, revealing the magnetic core materials. This distinction matters because the presence of ilmenite and magnetite is not just a curiosity, it's a potential signpost. In diamond exploration, these two minerals are classic heavy indicators, often found alongside garnet, chromite, and spinel. While not valuable themselves, They suggest that the local geology includes mafic or ultramafic rocks, possibly even weathered kimberlite. In lake settings, these minerals collect disproportionately in drop-offs and sheltered shallows, making magnet tests one of the fastest ways to triage raw material in the field. However, magnetic attraction alone isn't diagnostic. Plenty of iron-rich waste rock can mimic the same behavior. That's why visual correlation is key. Do the magnetic grains appear angular, glassy, or dense? Do they occur with transparent or colored fragments? A black sand cluster that includes angular red or purple grains points toward garnet association, which is far more suggestive of gemstone proximity than pure magnetic sweep alone. One overlooked test is magnetic separation post-rinse. After initial sweeping, wash the residue and retest. True indicator minerals will remain magnetic even after surface grime is removed. Iron-stained quartz or organic debris, by contrast, will often lose their false positive stickiness. A final trick: try suspending the magnet beneath a transparent container and gently pass your sample above it. This inverted approach minimizes contamination and allows you to observe particle behavior against gravity. True heavies drop faster and stick longer. With this rapid assessment method, you'll begin to see patterns. Certain shorelines consistently produce denser, more magnetic finds. Others offer none. But even if magnetism leads you to a good zone, you'll still need a way to isolate the truly exceptional. And in lakes without flowing water, how do you pan for gems without a creek? The answer lies in adapting the classic gold pan for a silent, still water context. Panning without current seems paradoxical. After all, flowing water is what traditionally separates light from heavy, winnowing gold or gem concentrates through turbulence. But in a lake environment, the principle still holds if you create the motion yourself. It requires slower cycles, finer control, and absolute patience. The reward is access to sediment layers most people ignore. Those just below the surface, where heavy mineral particles accumulate in still water and where mechanical disturbance, not flow, becomes the separator. Start with a wide, shallow pan, ideally 14 to 16 inches across, with well-defined riffles. Fill it a third of the way with sediment from your selected zone, focusing on dark sand, compact silt, or gravel-rich material from drop-offs or benches. Then, instead of aggressive swirling or shaking, use a slow, circular motion while tilting the pan at a shallow angle. Let water enter gradually from the edge, agitating only the topmost layer. You're not driving off fines through turbulence. You're coaxing light materials to float while heavy grains settle downward. This method, often called still panning or float skimming, rewards finesse. Periodically stop, allow the water to clear, and scan the lower margin of the pan for a band of dense particles. True heavy minerals like garnet or spinel will hug the bottom riffles. Quartz will shift upward and off. If you observe a black or rust-red streak forming a crescent near the base, particularly with a peppering of small, angular crystals, you're likely concentrating true indicators. For finer work, use a mini sluice or portable classifier. A compact sluice, operated with hand-poured water from a jug or a small siphon, lets you mimic creek-like conditions in bursts. Position it at a slight incline over a tub or tarp to recapture runoff. Pour samples slowly and observe retention in each riffle. This method isolates heavies while conserving material, allowing for reprocessing if valuable grains are spotted. It's especially effective when working with micaceous silt or beach sand, where flat particles otherwise interfere with traditional panning. A finer grain strategy uses sieves. Classify your sediment through multiple mesh sizes, typically number 20, 0.85 mm, and number 40, 0.425 mm. Focus on the under 40 fraction, which tends to hold the most challenging but promising concentrates. Once sieved, Use a bulb pipette or small spoon to isolate grains showing unusual luster or color. These are then set aside for dry testing, UV, conductivity, or displacement, as they often carry the subtle indicators missed during coarse sorting. Keep in mind, the goal isn't to find a finished gem in the pan, it's to locate an anomaly field. If even one grain in a full pan shows promise, it flags that location for systematic follow-up. Over time, repeated sampling across a grid will tell you whether a pocket exists or whether it was a fluke. Without flow, still water panning is slower, but also quieter, less contaminated, and more revealing in sediment-controlled environments. And once those first vivid grains emerge, deep red garnet, metallic black ilmenite, or translucent green fragments, the question shifts. What exactly are they saying about your lake's mineral history? To answer that, you need to listen to the supporting cast. Indicator minerals that don't make headlines but tell the real story. They're rarely what people come looking for, but indicator minerals like garnet, spinel, and chrome diopside are often the loudest voices in the sediment chorus. They don't carry the price tag of diamonds or sapphires, yet their presence, shape, and chemistry map the very conditions that allow precious gems to exist. When these dense, often colorful grains show up in lake sediment, especially together, they signal upstream rock types that may host higher value material, even if only in microscopic or weathered form. Begin with garnet. Most lake source garnets are almandine, a deep red to purplish species common in metamorphic terrains. While not typically gem-grade, their angular shape, vitreous luster, and density make them unmistakable in a fine concentrate. If you find rounded garnet grains with a frosted surface, you're likely near the tail end of their transport journey. Weathered and abraded, perhaps not worth chasing further. But sharp-edged fragments, especially in clusters, imply proximity to the source and minimal reworking. In glaciated zones or ancient terrains, this could mean you're standing on or near a secondary deposit zone, where materials have only been slightly shifted from their parent rock. Spinel, by contrast, is a denser signal, typically found in high-grade metamorphic and some ultramafic settings. Spinel shows up in lake beds as dark red-black, or occasionally blue grains with a dull luster but significant heft. Its density, often over 3.5 g/cm superscript 3, makes it stubbornly persistent in panning. While gem-quality spinel is rare in the wild, any natural spinel fragment in lake sediment speaks to a specific geological recipe. In many cases, it suggests the past presence of mafic rocks or serpentinized belts upstream. Exactly the kinds of settings that may also yield jade, chromite, or even diamond indicators. Then there's chrome diopside, a grass-green, slightly brittle mineral that may appear in fractured shards or tabular flakes. Its green hue and semi-translucent body can be mistaken for emerald by the untrained eye, but it scratches easily and lacks the toughness to cut well. Still, its meaning is profound. Chrome diopside is a classic trace companion of kimberlite-hosted diamonds. Its presence, especially alongside pyrope garnet or ilmenite, strongly suggests that some portion of your lake's feeder system runs through diamond-favorable terrain. Alone, it's not proof, but it deserves serious follow-up. What makes these indicators powerful isn't just their mineralogy, it's their suite. Finding one is suggestive. Finding 3 or more in a sample is a flag. Each points to a different condition: high-pressure formation, mafic chemistry, or ultra-stable density. Together, they form a geological fingerprint, whispering that the lake is more than just a sediment sink. It's a passive trap collecting centuries of upstream erosion. Once these indicators are recognized, the next move is not to dig deeper, it's to test smarter. How can you separate a truly dense candidate from one that just looks the part? The answer lies in testing weight, even without a scale. With just water and patience, a lakeside field test can yield powerful results. Weight in hand offers the first clue, But for real confirmation, you need a density check. Something that speaks not to size, but to the mass packed within. Fortunately, specific gravity testing can be done right at the lakeshore with nothing more than a cup of water and a bit of care. When properly applied, this displacement test can distinguish quartz, density 2.65 g/cm superscript 3, from garnet 3.8 for 0.2, spinel 3.5 for 0.1, or even rough diamond 3.52. It won't pinpoint exact values, but it will quickly flag what's too light to bother with and what might demand further scrutiny. To begin, select your candidate stones, those that pass luster, magnetism, and panning criteria. You'll need a small container of water, ideally with graduated markings, a fine string or mesh bag, and a way to weigh or estimate volume. Though precision can wait, tie the specimen with string or suspend it in a small mesh pouch so that it hangs freely in the water without touching the sides or bottom. First, measure the volume of water it displaces. This gives you the volume of the stone. Then, measure its weight dry, or simply compare by feel if you're in the field and working without a scale. A denser stone will displace relatively little water for its weight. Here's where experience becomes tactile. Two stones the same size can feel radically different in hand. A quartz pebble may float lightly in the palm. A garnet of the same size will press downward with a decisively greater force. Practice this weight intuition by comparing known samples. Collect quartz, feldspar, and magnetite in roughly equal sizes and learn the difference by repetition. Over time, your hand becomes calibrated, your judgment faster and more reliable. You can also reverse the test. Take a suspiciously heavy stone, measure its displacement first, and then estimate whether the weight feels appropriate for that volume. If it seems too heavy, you might be holding garnet, corundum, or even something more unusual. In jade hunting regions, for example, nephrite often tricks collectors because of its waxy luster and subtle green tones. But it also feels denser than it looks, often over 3.0 g/cm superscript 3. Recognizing this incongruity, appearance versus heft, is a field skill that turns missed stones into recovered value. For microsamples, use a syringe or pipette to measure displacement in milliliters. Place the grain in a narrow graduated tube. Note the rise in volume. Then dry and weigh the particle on a portable scale if available. Even this simple method can reveal outliers. Dense black grains that aren't magnetite, or small translucent shards whose density exceeds quartz. In gem testing, gravity never lies. But gravity is only part of the picture. Some stones mask their value by wet surface effects, particularly those that rely on internal structure to reveal their character. To unlock their true potential, you must dry them and expose them to invisible light. The next revelation comes not from weight, but from glow. The moment a promising stone comes out of the pan, it often looks better than it is. Wet surfaces amplify luster, deepen color, and mask surface flaws. But for UV fluorescence testing, this surface moisture does more than mislead the eye. It suppresses the very signal you're trying to detect. Water interferes with ultraviolet response by scattering light and reducing the penetration depth of the UV beam. So, the classic mistake many beginners make is testing lake wet samples under UV and dismissing them as inert when they might actually hold a hidden glow. To correct this, every sample intended for fluorescence screening must be thoroughly dried. Sunlight is sufficient, but controlled drying in shade is preferable, especially to avoid thermal fracturing of more fragile stones like opal or zircon. Once dry, use a long-wave UV lamp, ideally 365 nanometers wavelength, for general screening. Shine it in a darkened environment. A shaded container or small field box works well. And scan across your sample slowly, observing not just color but intensity and uniformity of fluorescence. Diamonds, for instance, often fluoresce blue under long-wave UV. though the strength varies by origin and impurity content. This trait is not diagnostic alone. Plenty of synthetics and simulants glow blue, including some cubic zirconia, but in conjunction with density and luster, it's a valuable supporting clue. More telling is when you see a mix of responses. One grain glows blue, another inert, another red or green. This diversity often reflects mineral variety, which in turn signals a more geologically active or mineral-rich zone. Some garnets show dull orange fluorescence, especially grossular varieties, though almandine types typically remain inert. Spinel, on the other hand, can surprise you, especially the magnesium-rich varieties that fluoresce pink or red. Zircon sometimes fluoresces golden yellow, but beware, many synthetic zircons and heat-treated stones mimic this behavior. If you suspect zircon, move on to cross-check with weight and luster. The real test is consistency. Does the sample fluoresce on all surfaces, or only on freshly broken edges? A consistent, even glow suggests intrinsic structure. Patchy or edge-only fluorescence often indicates coatings, dyes, or heat treatments, signs of artificial enhancement or mislabeling. In lake contexts, naturally occurring fluorescence is rare enough that any strong glow deserves careful follow-up. Take photos under UV whenever possible. Later, you can compare glow patterns to lab references or send samples to a gem lab for spectroscopic analysis if a stone warrants serious scrutiny. Field logs should include fluorescence observations alongside weight, luster, and location, not just for record-keeping, but because UV behavior often helps track indicator mineral zones across a wider area.